Hi everyone, my name is Dr. Jiao. I am an associate professor from University of Adelaide. Today, I want to share with you of my research, why I'm interested in this type of research, what we can do, what my research can achieve, and how I perform my research. So the motivation for me to do my research is the excessive CO2 emission that's making our Earth becoming warmer and warmer, which led to many problems. And the fossil fuels are currently less and less. So in the future, we might run out of fossil fuels that was formed millions and millions of years ago. So how do we address these two problems? Where there is one quite simple solution. So think about where all those energy are coming from. I am putting here a diagram of all the energies that we can come across in our everyday life. So all these energies, they can convert between each other. But speaking of where all those energies from the Earth are coming from, they're all coming from the solar energy. So million and million years ago, the plants grown on the Earth, they are buried underneath, and then after high temperature and high pressure, they convert to fossil fuels. And then nowadays, we dig out all those fossil fuels and then transform that into other types of energy. So that's what happened in the past. Maybe the fossil fuels are becoming less and less, but the origin is always there, which is the solar energy. So my research is converting solar energy to fuels. So on this diagram, I show how the equation looks like. On the left-hand side of the equation is the solar energy or wind energy that's also converted from solar energy, and plus some feedstocks like water or carbon dioxide. These feedstocks can provide us with the hydrogen source or the carbon source. And then combining all these things together, we can produce synthetic fuels. So all these synthetic fuels, they will not run out because all the elements that make those synthetic fuels exist, and they will keep existing for a very long time. And by using this equation, we can also address the excessive CO2 emission problem because we take that into account of this equation. So how do we make this equation work? We need to use a special material called catalyst. Only by using this material, the feedstock from the left-hand side of the equation can be changed to the right-hand side, which are synthetic fuels. So catalyst material are really important. And in my research, how do I design a catalyst material? Well, I do it like playing with Legos. So at the beginning, I will select a reaction that I would like to work on. Is it the conversion from water to hydrogen, which is a type of fuel? Or is it the conversion of carbon dioxide plus water plus solar energy to synthetic fuel? So the synthetic fuels can include ethanol, methanol, everything that comprised of carbon, hydrogen, and oxygen, just to name it. So once the reaction is selected, I start to build models. Now on the top left corner, there shows a model that I built on the computer. Normally I do that in the computer, but sometimes I also configure a real molecular models like this. For example, the ball that I'm holding is a molecular model of fluorine. So it is comprised of 60 carbon atoms. It looks like a football. The only difference is that each of the point here is a carbon atom. So that is one example of the fluorine. I might construct using the same carbon atom. I might construct other models. I try to display it with this background. So here is a structure that constructed by carbon, but because of the configuration is now different, we call it diamond in real life. Okay, so with the different construction models, we can build different materials. After the material, the catalyst material is built, we then construct the reaction pathway depending on the beginning of which reaction that we selected. And then we calculate the energy along the reaction pathway. Analogy of the reaction pathway is you want to climb a hill. You start from the feedstocks like the hydrogen, carbon dioxide, nitrogen, for example. And on the other side of the hill is the product that you want to have, or the right-hand side of the equation that I just described. So from the left-hand side of the equation to the right-hand side equation is not that straightforward. Normally, the system needs to go through a reaction barrier. A catalyst material can help us to reduce that reaction barrier. And the lower the barrier is, the easier the reaction will happen. It's just like us climbing a hill. Well, if the hill is lower, then it's easier for us to walk from this side to the other side. If the hill is higher, like the Himalaya, then it's almost possible that we can walk to the other side of the hill. Okay, now after we calculate the energy along the pathway, depending on how high the reaction barrier is, and then we can make a decision whether the constructed material is a good choice or not. If it is a good choice, then we will send that to our collaborators who can synthesize this type of material and then test their performance. Okay, so this is why I'm interested in renewable energy research, how I do my research, which is building Legos on supercomputers, and how that might generate impact in the real life. I am the 2020 Young Tall Poppy, and I'm really happy to share my research story with you.